Crowley's study in the mean total cloud cover in octars for Leuters in 1987 using data from a large data set. The daily mean total cloud cover for all 184 days from the set is summarized in the table below. So remember, say 4 octars would be 4/8 of the sky covered in cloud. That's what an octar is. It's like an eighth. Whereas 0 octars would be none of the sky covered in cloud, and 8 would be the sky was fully covered in cloud. And what's happened is different values have been taken throughout the day, and then the mean value has been found. Presumably rounded or something after that to just give us these values. So one of the 184 days is selected at random, and we're asked to find the probability that it has a daily mean total cloud cover of 6 or greater. So we're interested in picking from one of these days. We can add up those numbers. This gives 132. And then if we divide by the total number of days, that will be our probability. We're going to write it to 3 significant figures, not least because although you can leave this, later on we're going to need to have it as a decimal to compare. So it's 0.717. Now this is the bit of the question I really like. So Magali's investigating whether the daily mean total cloud cover can be modeled using a binomial distribution. So just seeing, we've got some real live data here. Can we fit a binomial distribution to it? And this question really gets into depth now in whether it's going to be okay or not. And she uses a random variable x to denote the daily mean total cloud cover and believes that x follows this distribution. This is really interesting because 8 is the number of trials normally in a binomial distribution, but here it's like it's also the number of octars. So we're managing to use a binomial distribution in a slightly less conventional way, because a trial is like, can we're going to do it 8 times, are we going to get an octa every time? And it does, like, in theory, work out. So using Magali's model, find the probability that x is greater or equal to 6. And that is going to be 1 minus the probability that x is less than or equal to 5. So we want 6, 7, 8. So what we're going to do is minus 0, 1, 2, 3, 4, 5. That will leave us 6, 7, 8. And if you're using the same calculator as me, this is how you have to do it. Because the distribution binomial CD only deals with less than or equal to. So x is 5. N is 8, P is going to be 0.76. And we get 0.2967. Remember, it's 1 minus that. 2967. And that ends up being 0.703 to 3 significant figures. It's actually pretty close to what we had before. And we're also asked to find to one decimal place the expected number of days in a sample of 184 days with a mean total cloud cover of 7. So we can see in the actual data, we had 52 days. Now we're finding the expected number. So what it's actually going to be is 184 multiplied by the probability that x equals 7. Because if it was like, if the probability was a half, you'd expect a half of the days to have that cloud cover. But the probability that x equals 7 gives us the proportion of days that we'd expect. So go back out to, now it's going to be binomial PD. That's just for one value. 7. And we get 0.28118. And if you multiply these together, then it gives 51.73, which rounds to 51.7. Okay, again in good agreement. So explain whether or not your answers to B support the use of Magali's model. Can we use a binomial distribution to model it? And yeah, the answer is yes, because they're very close. So 51.7 is approximately 52. And I know that we can't actually, you can't actually have 51.7 days, but you could still write that down, just like the expected number of goals scored in a football game might be 0.5. They might be averaging a goal every 2 games. You can have a decimal there. You don't have to round it to like 1 or something. That would be misleading. So we can have it as a decimal and compare, but it's close to 52. and our 0.703 is approximately 0.717. So I wrote down that, yeah, Magali's model is, this supports us using Magali's model. This is where the question gets really interested in. So there were 28 days that had a daily mean total cloud cover of 8. For these 28 days, the daily mean total cloud cover for the following day is shown in the table. And what we see is that if a day had high cloud cover, then it tended to have high cloud cover on the next day. And in this next part of the question, we're kind of getting into some other aspects of the binomial distribution, because remember, events have to be independent in the binomial distribution, and it doesn't look like they're going to be, but we're going to look into it in more detail now. So find the proportion of these days when the daily mean total cloud cover was 6 or greater. Similar sort of thing as before. We're going to add these up. This gives 23. Now we're going to divide through by 28. So it's 0.821. And then comment on Magali's model in light of your answer to D. So what we see is that this value here, the 6 or greater, is 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 quite a lot larger than the 0.717 that we had before. Another way of saying this is if there was high cloud cover on a day, then the chance of there being high cloud cover again is greater than if there, for example, wasn't high cloud cover. And this means the events are not independent. So events are not independent. So the model may not be appropriate after all. You can get some really good predictions, but it doesn't mean that it's going to be actually a valid model, especially maybe for lower values or something like that. We had these excellent values, but now we've just shown that events are not independent, or at least there is definitely, yeah, there's definitely flaws in the model, and we just have to comment on that. So yeah, that's one aspect of this question I really like. So let me show you the mark scheme for this. So yeah, you need to say that they differ, or actually any one of these. So they differ. There's a different probability of high cloud cover for these days than the other days. Independence does not hold. For me, that is the crucial one. That is the thing that this question's getting at, and therefore it may not be suitable. Okay, enjoyed that. I hope you did as well.